Okay, so on Friday we started looking at examples of problem solving using work energy theorem. So just a quick review, okay? Work energy theorem says that work is a change in mechanical energy, either potential or kinetic or both, but we're only going to deal with problems that are either potential or kinetic energy, okay? And so that would be EF minus EI. What's the other way to calculate work? Multiply two things, force and distance, right? Okay, so work energy theorem essentially boils down to this. Work is force times distance, and it is also the change in mechanical energy. Okay? And so all of our problems are going to break down to either having work equal to a change in energy or having force times distance equal to a change in energy, okay? One or the other, and then we're going to be manipulating and solving. Right? So this here was an example of a question where what kind of energy was changing? Kinetic. Okay? How do we know? It talks about speed. In fact, it says there is a change in speed. It goes from rest to this speed, to 4 meters per second. It doesn't mention anything about it being lifted off the ground or going up a ramp or anything like that. So there's no change in potential energy, just a change in kinetic. So that's like the biggest challenge that we have to get from the context of the question. So we say work is a change in this case, kinetic energy. Right? Our givens here are the mass of the rock, 550 kilograms. Okay? The initial speed, 0 meters per second. Okay? The final speed, 4 meters per second. And the distance over which the tractor pushes the rock is 25 meters. Okay, now that I've got my givens and I know what type of energy is changing, I look at my givens and figure out, all right, what do I have to write down as formulas? The question wants to know force. Well, that tells me that I'm not going to be using W, I'm going to be using force times distance, right? And that would go along with the fact that I was given distance. Everybody with me here? Okay. If I want to calculate the change in kinetic energy, then I'm going to set up the kinetic energy formula using my final kinetic energy minus my initial kinetic energy, which I probably didn't even need to write. Why? Yeah, my initial kinetic energy is 0 because it does say that the object is at rest. If you're at rest, you don't have any kinetic energy. All right, so that means force times distance equals 1/2 times mass times the final speed squared. All right, I'm looking for force. How do I get force by itself? Right, divide by distance. Okay, right now I'm multiplying force by distance, so if I want to move something, I do the opposite. Okay, what I do to one side, I do to the other. Now I've got my formula for force. Okay, now I just need to plug in my numbers. So force equals 1/2 times 550 times 4 squared, okay, divided by 25 meters. Okay. Everybody with me so far? Sorry, I should have fired up my calculator previous to this. Okay, so 0.5 times 550 times 16, because that's 4 squared, okay, divided by 25. So, going to use 176 newtons worth of force. That's actually not very much. Okay, like you don't need a tractor for 176 newtons. It just worked out that way. What does a tractor spend most of its energy working against? Like the actual energy or the actual force needed to move the rock, to accelerate the rock, if there was nothing else involved, would have been 176 newtons. You or I could have done that. Okay? But what makes it hard to move a rock? Gravity and friction. Yeah, the two of them working together, that's what makes it hard to move a rock. Like if the rock's not round, you're not getting it to go anywhere, right? It's just, it won't slide. Okay? It's not so much that it's big and heavy. If this thing was set, if this rock was set on a piece of frictionless ice, you or I could walk up to it and go like this. give it a little push with our fingers and off it would go. Okay, 176 newtons is not a lot of force. Okay? But in these kind of perfect physical world examples, that's what it ends up being, because getting something to move is actually not that hard if you take out all the real world resistance that would normally be there. Okay, questions on how that works? Okay, so all work energy theorem questions essentially work the same way. So once you get the pattern, you can do any of them. Okay, and the pattern is, write the givens, figure out what type of energy is being changed, kinetic or potential, by looking for either a change in velocity or a change in height. Set up work energy theorem formulaically, so force times distance equals the change in energy. Manipulate, plug in, and solve.
So is it always like the setup going to be like force times distance equals either like kinetic or potential energy equation, or no?
Pretty much. It could be easier than that if the question actually tells you the work. Okay? If it says this much work, or asks you how much work is being done, then you might not even need the force times distance, or you might not even need the change in energy part, right? So it would depend. Sometimes a question is actually that easy. It says calculate the work, or here's the work, calculate the distance. Okay? So sometimes they're even easier than this. Like this one. It's just asking you for how much work is being done. Okay? So let's have you copy this one down and give it a try. So givens, type of energy, work energy theorem. Okay, so work is the change in energy, and then solve. Right? You don't have to actually do any manipulating on this. All right, so work energy theorem problem. Okay, first thing we want to do is write down our given. So a mail carrier picks up a 10 kilogram package. What did they just give me there? Mass. Okay, on the 3rd floor of a building, 30 meters above the ground. What did they give me there? They gave me the initial height. Okay, and delivers it to the 10th floor, which is 100 meters above the ground. Final height. Okay, how much work is done? All right, they don't mention force, they don't mention distance. Do I need to even write force times distance in this one? I don't. Okay, what kind of energy is being changed in this problem? Right, this is a change in potential energy. All right, so this is as far as I need to go in terms of looking for any other formulas. Work is the change in potential energy here. Okay, so like we said before, I won't need force and distance, which is good because they didn't give it to me anyway. Right? The other way to calculate work is to calculate the change in energy. So m times g times h final, or my final potential energy, minus my initial potential energy. M times g times h initial. Now on this one, I actually have an initial energy. Okay? On all the other ones, we started from nothing. But on this one, I actually do have an initial energy. Somebody else took the package to the 3rd floor. The mail carrier only had to take it from the 3rd to the 10th. So, if I'm going to calculate this, now all I have to do is plug in my numbers. I don't even have to manipulate anything. It's already set up to calculate work. So we'll have our 10 kilograms times g, which is 9.81, times our final height, 100, minus 10 times 9.81 times 30. Now, if you're a really sharp math student, you may have noticed a shortcut. What would the shortcut be?
Just times 130.
Not 130, 70. Yeah, you could have just done the difference in heights, okay, and that would have given you the change in potential energy as well. It only works for potential, which is why I don't bring it up when we're doing kinetic, because in kinetic it's squared and there's a half in there, it messes things up. Okay, but for this one here, you could just do this, m times g times the change in height, and you get the right answer. Again, that doesn't work for kinetic. You can't go change in velocity and then square it. That's different. Okay, but it does work for these. Okay, if that just went like this for you, forget I said anything. This works just fine too. Okay. All right, when we plug this into the calculator, we got 10 times 9.81 times, not minus, times 100, okay, minus 10 times 9.81 times 30. All right, so this mail carrier got their steps in and burned some calories. 6,867 joules worth of work being done in carrying the 10 kilogram package from one floor to the next. Okay, questions there? All right, so works pretty much the same even if it's potential energy, right? It's still final minus initial, okay, and we set it up. Okay, now, no, I don't want to talk about that yet. We'll do this one first. Okay, so this one we got a bulldozer, okay, pushing a truck from 2 meters per second to an unknown velocity. We know the mass of the truck. We're looking for its final velocity. That is its final velocity, so you can check and see if you do it right. Okay, 3.16. So give you a couple minutes on that. Same idea as before. Okay, so let's do it the same order we do them always, okay? Bulldozer does 7,500 joules of work. So they told me the work. Okay, and it pushes a truck from a speed of 2 meters per second to an unknown speed, which is what they want us to calculate. Truck's mass is 2,500 kilograms. Okay, what kind of energy is changing here? Kinetic. All right, so we can establish then work energy theorem. Work is a change in kinetic energy. All right, here's where you can make the algebra a little bit easier. Right? We know the work, so we don't have to put force times distance into this one. They told us what that equals already. All right, so we know work equals the final kinetic energy minus the initial kinetic energy. Up until now, that's always been 0, so I've just written the formulas in and then crossed off the initial part. This time there is an initial energy. And what I want to calculate, VF, is part of this. So I want to get this by itself. What do I do with EI? Add it, yeah. Bring it over to the other side. Here's why that makes sense if you're like looking at this mathematically and it doesn't make sense. Here's why it should make sense like intuitively. Work is the change in energy. So if I'm looking for the final energy, it would be the initial plus the change, plus the work, right? I have this much energy, then I do a bunch of work, now I have this energy. Okay, so I'm going to add the initial energy over here. So work plus EI equals EF. All right, now I'll expand it out. Got some of my other work down here. That's a spoiler. We don't want to see the end yet. All right, so we've got work plus 1/2 MVI squared equals 1/2 MVF squared. Okay, it's a little easier to move it before you have it expanded. Okay. All right, I want VF by itself. What do I have to do with the half and the M? Divide them over to the other side. Okay, that gets me VF squared. I just want VF, so what do I have to do the whole thing? Square root. Okay, so what we're looking at here is that our final velocity will equal 7,500 joules, the amount of work done, minus 1/2 times 2,500 kilograms times 2 squared divided by 1/2 times 2,500 kilograms. Okay, just plugging in all my numbers.
Wouldn't you add the?
Sorry, add.
Yeah.
Because I wrote it add over there. So I should write that there. Okay. So if I plug all that into my calculator, one piece at a time, so 7,500 minus 0.5 times 2,500. I keep doing minus. I'm such a negative person today. 2,500 times 4 squared. Okay, and then I'm going to divide that by 0.5 times 2,500. And then I'm going to what? Square root. Okay, 3.16 meters per second would be our final velocity. Our final speed, I should say. Okay. Everybody all right with that? Okay. Have any of these deviated from the pattern? We've done every single one of these exactly the same way. We wrote our givens, we established what type of energy was being changed, we set up the work energy theorem, okay, and then we manipulated, plugged in numbers, and so on. Okay. Always the same set of steps. So once you have that pattern, the trickiest thing is figuring out what kind of energy is being changed. Okay, so what's on here is that set of steps I just talked about. So solving work energy theorem questions involves, okay, writing out the givens, okay, knowing that work is a change in energy, and that sometimes that means force times distance equals the change in energy, okay. We first identify, or sorry, second, write out the givens, then identify the type of energy being changed. Is it m times g times h, or is it 1/2 mv squared? So is it kinetic because of a change in speed? Or is it potential because of a change in height? Set up the work energy theorem. Okay, work's a change in energy. Force times distance is EF minus EI. Okay, and that could be either kinetic, like you see here, or potential, like you see over there. All right, I'm assuming you guys some of you are wanting to write that down, so I'll stop. I'll go back up to here, and then I'll slowly scroll it down while you're writing, because that's not in your notes package. Okay, so for this one here, they're saying a person is using an unknown force, okay, so this one will probably need the force times distance part, okay, to lift a 50 kilogram mass to a height of 1.5 meters. Now there is a little bit of a trick to this one, okay. When you're lifting something, the height and the distance over which you exert the force are the same, okay. So you're given one number that has to serve two purposes in this question. Okay? The work is being done over 1.5 meters, but that's also the height change in the question. All right, so as we said, the trick here is to understand first off that the height and the distance are both 1.5 meters because we're talking about something moving vertically. Okay? That wouldn't be true if I was pushing it up a ramp. Okay, if I was pushing this thing up a ramp, the distance would be the length of the ramp, and the height would be the change in height, vertically speaking. Okay, then they wouldn't be the same. But if you're just lifting something vertically, distance and height are the same number. Okay? Now, because this is talking about a change in height, we're talking about a change in potential energy. Okay. The other number we were given was the mass, 50 kilograms. So, I didn't erase all my work. Okay, so work is, okay, a change in potential energy. So I have force times distance, which equals m times g times h. Now, they want to know the force. If I divide both sides by distance, and height and distance are the same number, what do? So what I'm left with is the force used is equal to m times g, which we haven't talked about yet. But that is how you calculate the force of gravity, or your weight. Okay? Because probably up until now, you thought your weight and your mass are the same thing. It's another one of those things our society has messed up royally. Okay? When you step on the scale says, "Get off, get off!" That's what it says when I step on it anyway. Okay, but okay, what it reads is your mass on the screen. What is it actually measuring? It's measuring your weight. Okay, so here's how a scale works. A scale is a big spring, right? So you step on the spring and you squish the spring. You exert a force over a distance. Okay. Everyone with me on that? You put elastic potential energy in the spring of the scale. Well, the force that you're using is the force that gravity pulls down on your mass with, your weight. Okay? So your mass is actually how much of you there is. Okay? It's a measure of how much matter you contain. Your weight is the force of gravity pulling on that mass, which is why if you go to the moon, you weigh less. Is there any less of you? No, your mass is the same. So you want to lose weight? Just go somewhere where gravity is smaller. And you'll weigh less. Okay, that's, again, it's all about weight loss. Everything is like, especially in the new year, that's all we'll be bombarded for the month of January with stuff about weight loss. You're not losing weight. You're losing mass. Weight goes along with that because there's less of you for gravity to pull on. But it's mass that you're losing. It just doesn't sound as cool. Like, mass loss! What? What is that? Like nobody ever, it doesn't mean as much. But it's true, okay? You're not actually losing weight, okay? You can change your weight just by, I mean, if you had something, a scale that was this accurate, you could lose weight by going from the basement to the top floor of your house. Okay? You move a little bit further away from the center of the earth, you weigh a little bit less. Not a lot, like we're talking millionths of a gram here, but okay, it's true. Your weight is actually dependent on the acceleration due to gravity and the force of gravity. Okay. So if I want to calculate this force, all I have to do is go m times g. So I take that 50 kilograms, I multiply it by 9.81, I should get 490.5 newtons as the force used. So if I want to change something's potential energy, all I have to do is exert a force equal to its weight in order to lift it. So here's a fun trick you can play on people. Because this really, like, if someone ever asks you this, it's a really indelicate question, right? You go somewhere and someone's like, how much do you weigh? So what I say is, I weigh 785 newtons. What do you weigh? And then they kind of chuckle awkwardly and walk away. And I call that a win. Because I'm not a social person, and probably would rather not talk to someone with such social ingraces. Okay, and yeah, and I've also told the truth. That is my weight. You asked, I told. It means nothing to the average person to say something in newtons because they have no idea what you're talking about. They think you're weird, which means less people will bother you. Okay? Or you can also say, do you mean my mass? Because they're different things. And you can give them the big lecture and they'll also go away. So it's totally up to you how you want to handle that one. Okay? But you should make them feel awkward for asking such an indelicate question. All right. Here's what I was talking about. If I have a question where something's being pushed up a ramp, now the force is acting over the length of the ramp, but the height is a different number. Okay, so the height and the distance are only equal if you're lifting something vertically. Okay, in this case, we're pushing it up a ramp, so the force acts over the length of the ramp, and the height will be a different number. Right? So give this one a try. See how we do. We're looking for how much higher the box is than once it's at the top of the hill. If you start at the bottom of the hill, what is your initial height? Right. All right, so we have the mass of the box is our first given. It's 35 kilograms. Okay, it's being pushed up a hill by a force of 150 newtons. So they gave us the force. Okay, and that's over a distance of 25 meters. In other words, the ramp is 25 meters long. Right? How much higher is it when it's at the top of the hill? All right, so that indirectly tells me the initial height is 0 meters, okay? And the final height is what I'm looking for, okay? How high is the top of the hill? All right, so I've got mass, I've got force, distance. What type of energy is being changed here? Potential energy, okay? The height of the box is changing, okay? Doesn't mention anything about speed change, just height change. All right, so since I was given both force and distance, I'll have to use them, okay? And that's going to equal my change in potential energy, which will be EP final minus EP initial. But what's my initial potential energy? 0. All right, so that means force times distance equals m times g times my final height, which is what I'm looking for. So in order to get final height by itself, what do I do with the m and g? Divide them over to the other side. All right, so that leaves me with the final height. When I plug in my numbers, that'll be 150 newtons times the 25 meter distance divided by 35 times 9.81. Okay, that should leave me with 10.9 meters. Now, when you punch that into your calculator, you do have to be mindful, okay, that you are doing the top divided by the bottom and not all in a line. Okay, so we got 150 times 25, okay, then divide that by 35 times 9.81. So 10.9 meters is our height of the ring. Everybody all right with that one? All right, it's 9:32. We'll take a 5-minute break. You have to take it within the room, obviously. I can only let one person out of the room at a time. Okay, but, okay, take a 5-minute break and be back at this at 9:37.
Can I go flip my work?
You can. You need to go after her, you're next. One. This would be about as tricky as they would ever get. Okay, and I don't mean it's like contextually tricky, it's like this is the trickiest of the manipulations you might have. Okay, and you've already done one kind of like this. Okay, so we're looking at pitcher throws a ball, we know the mass of the ball, we know the force that the pitcher can exert. Okay, distance, we're looking for the final speed. What are we going to assume the initial speed is since they didn't tell us? Right. Okay, ball starts in the glove. All right, let's look at this one. So if we're writing down our givens here, we know the mass and the force right off the bat. Okay, the mass is 0.250 kilograms. If they gave that to you in grams, if they said 250 grams, would you be able to use that or would you have to convert it? You'd have to convert it, okay, because joules are a kilogram meter squared per second squared. It has to be in kilograms. Okay, we know the force is 300 newtons. Okay, and we know that the force is exerted over a 2.2 meter path. Now, is that path a straight line? No, and it doesn't have to be either. It's just the distance over which the force is exerted. I mean, in a baseball pitch, there's all kinds of changes in direction of the ball, right? It bends the person's arm back. Okay, it's not a perfectly straight line, okay? But it doesn't have to be. At what speed will he release the ball? And we already said we assume, since they didn't tell us otherwise, and from the context of the question, that VI would be 0. Okay, what kind of energy is changing here? Kinetic. Okay, so force times distance, we're going to need that this time because they didn't tell us the work and they gave us force and distance, is going to be equal to 1/2 mvf squared minus nothing because we said VI was 0. All right, so let's get rid of that. Okay, looking for VF, so I'm going to divide both sides by half of m and square root. Okay, so that really is like the trickiest of the manipulations unless you actually had an initial energy that you would have to bring over as well, okay? Which you've already done one like that. So we would have a force of 300 newtons times 2.2 meters, okay? And that's going to be divided by 1/2 times 0.250. So we punch that into our calculator. Okay, we've got 300 times 2.2, which is 660, okay, divided by 0.125, that's half of 0.250, and then square root that. Okay, 72.66 or 72.7 meters per second, which, to give you an idea, is really fast. 261 kilometers per hour. Nobody throws a ball that fast. Not even a major league pitcher would do that. What are we looking at here? Yeah, that's 163 miles an hour. Okay, a really, really strong, well-techniqued major league pitcher might throw 105. Probably not, but like that would be ridiculously fast. So this would be a superhuman robotic arm. All right, questions on how that one worked? Okay, so here's the plan going forward up until we start our Christmas holidays. Okay, today and tomorrow we're going to work on work energy theorem stuff. On Wednesday, sorry, we're going to do a lab on work. Thursday, I'm going to introduce conservation of mechanical energy, which is not going to be a whole lot different than this. Okay, Friday we'll do our unit exam review, even though we haven't really done conservation of energy and efficiency yet. Okay, Monday, lab on conservation of energy. Tuesday, finish up conservation of energy. Wednesday, efficiency. Thursday, test. Friday, go over test. Okay, that's what we're doing going forward. So we will start our last unit when we come back from Christmas, not before, right? And we actually have like a decent amount of class time to do it. We actually have like 2 full weeks to actually do that unit. But I'm going to try and get us some final exam review time in class, because yours is one of the first finals and you won't have a lot of time to come see me for help after classes end. So my intention is to teach that in about 8 days, okay? 8 or 9 days, have an exam on like the Thursday of that second week back, and then have Friday to go over that unit exam, and 3 days the next week to do final exam review of chemistry, biology, and physics. We won't bother reviewing the last unit because we will have just reviewed it, okay? And just done, and then be fresh in your mind. Okay, so that's the plan. At least that's where it sits in my mind right now. It has to be flexible, which is not easy for me because I'm a science guy. I don't think flexibly. Very linear. Okay. All right, just so you're aware. Okay, we talked about this one. This was that really like dark day. Hitting the brakes. Brakes is work energy theorem. See what you remember. Okay, try that one. Okay, so for this one, all right, we've got that the car applies its brakes with a force of 10,000 newtons. So what did they give us there? Force. Okay, it slows from 20 meters per second to 6 meters per second. All right, they give us 2 speeds. Which one is initial? The 20. Okay, and then the final is 6. Okay, if the car's mass is 1,700 kilograms, how far does it travel? So we're looking for distance. What kind of energy is being changed here? Kinetic. Okay, so that's going to mean force times distance equals, okay, 1/2 mvf squared minus 1/2 mvi squared. And we have both of those. Okay, we have some initial and we have some final kinetic energy, and that's fine. We're looking for distance. So what do we have to do with F? Divide it over to the other side. Okay, when we do that, we have to keep this in mind. We want to do the top before we divide by the bottom. Okay, so plugging in our numbers then, we have 1/2 times 1,700 times 6 squared, minus 1/2 times 1,700 times 20. So this is going to give me what kind of number? Yeah, it actually comes out negative if you forget something. And you would honestly forget it because I haven't told you it. Which way does braking force act? If it makes you slow down, it's a negative force. Because if you write the distance is negative, first off, it can't be. Distance is scalar. Okay? But secondly, you said that by applying the brakes, you went backwards. That would be violent on the person in the car. Be great for the kid in front of the car. Bad for you in the car. To violently lurch from going 20 meters per second backwards, hey, that would be really awful. Okay, so that's obviously not what happens, and we can preserve that by making sure we understand a braking force is actually backwards and is thus negative. In the end, we're solving for distance, which can't be negative anyway. So 0.5 times 1,700 times 6 squared minus 0.5 times 1,700 times 20 squared Okay, it gives me negative 309,400 joules. Okay, and then I divide that by negative 10,000. And I get 30.94 meters. 30.9 meters. Okay.
Even though like you get the same answer and stuff, but for like the final velocity or whatever, why wouldn't it be a negative if the car's slowing down?
Well, if it's negative, that means that applying your brakes made you go backwards again,
Okay.
right? Like this has to be positive because it doesn't tell us the car moved backwards. It said it slowed down, right? I mean, and brakes never make a car go backwards. They exert a force backwards, that's what stops us, but they don't propel something backwards. That'd be different than running into a bungee cord, which could propel you backwards. It would also act as a braking force, but would then propel you backwards afterwards. But, yeah? That's the weird thing about brakes, right? Is we don't picture brakes as producing a negative or backwards force because we don't go backwards. All right, we'll leave it at that for today. I got to come around and wipe down all those desks, so if you can clear them off, I will come around and do that.